Hi, everyone. We're CellSight. We are a contraband electronics detector. Our faculty advisor was Dr. Mohammed Salem. Our industry advisor was Mr. Chris Stewart. Our client was Lieutenant David House from the Sonoma County Jail. And our website is www.cellsight.net.
I'm Daniel Gill.
I'm David Story.
And I'm Blake Zuniga.
So we're going to go over a little bit of the overview of this project, which consists of the main problem, the current existing solutions, how this project actually works, our solution, the requirements, and then finally an in-depth look at some of the logistics and the hardware that we designed for it.
The problem that we are addressing is contraband in jails and prisons, which has been an issue throughout history. As technology has progressed, so has the threat to our officers within jail systems because of the capabilities of the illegal contraband that has been smuggled in. Cellular communication devices that are acquired illegally in prisons and jails have allowed prisoners to plan and execute prison riots, control external criminal networks, and even coordinate homicides of witnesses and public safety officers. Cellular devices are easily hidden and hard to find, as they can be hidden within the prisoner's cell. Devices are typically found through detection processes such as spectrum monitoring, through physical searches, and by putting inmates through x-rays. We plan on developing a system to aid our officers with this issue through a different method known as nonlinear junction detection. There are systems out there that already use this method, however, they are not easily accessible to our officers.
So here are some of the existing solutions currently out in the market. We see all these devices are capable of detecting nonlinear junctions, but they're also very big and bulky, and they're very expensive, making them less affordable to smaller jails.
The Nonlinear Junction Detector, or NLJD, is a device that illuminates a small region of space with high-frequency RF energy. Any nonlinear junction in the vicinity, for example the PN junction, will receive this energy, and because of the asymmetric response of the junction to an electric field, it will rectify it and re-emit some of it on multiples of the illumination frequency. These are known as harmonics. The detector has a sensitive receiver tuned to these harmonics, as well as appropriate processing and displays to make their presence known to the user of the device. Because the basis of almost all semiconductor electronics is the PN junction, an NLJD is correspondingly capable of detecting almost any unshielded electronic device containing semiconductors, whether the electronics are actively powered or not. By measuring and comparing the power levels of the harmonics, we can differentiate an electronic device from other base materials that may be present within a jail cell. The graphs show the differences in harmonic response from a nonlinear junction and other materials.
So to make our solution stand out from the other devices that we show, we want to make it a little more portable and more user-friendly for anyone who's using this device. Furthermore, to reduce the costs, we want to utilize a combination of both custom-made and off-the-shelf components, which will reduce the overall development and cost. Finally, we want to implement a modular system for our device because that will allow for future performance upgrades that will enable for better detection with these devices.
So these are our market requirements. Just to highlight a few, the product must be less expensive than current commercial products. The product must be fairly accurate in differentiating a nonlinear junction from other materials. And the product should provide detection without audio or no engineering requirement, the knowledge required. And these are engineering requirements. Again, just to highlight a few, the prototype should be at least or under $750. Should be able to differentiate between an electronic junction, a metal, or any other kind of non-metallic object, and it should last at least 4 hours, at least have 4 hours of rechargeable battery life.
In order to confirm the feasibility of our application, we ran preliminary tests using test equipment that would emulate the components within our own system. We conducted the test with a cell phone, a sheet of plywood, and a sheet of aluminum and recorded the measured power levels of the reflected harmonics. The graphs represent the measured harmonic power levels of our test materials relative to the open space measurement. This test showed us that the results were consistent with our expectations and that the cell phone produced a harmonic response that was differentiable from the other materials. As the theory suggests, the second harmonic of the cell phone is greater than the third, and it is to note that the aluminum sheet produced a similar result. However, we presume that software would be able to handle discerning the two because one difference is much greater than the other.
So looking at our system from the high view, it kind of is composed of two systems, that being the RF side, where we have a transmitter module and receiver module that generate and receive the harmonics that are in the test signal that's sent out to the phone. And then finally, on the other side, we have kind of the processing and user interface side, where we are able to get input from a user and then to control these tests. And on top of that, we also have a rechargeable battery and voltage regulator that powers the whole system. So looking at this a little closer, one more slide, please. We want to first look at the transmitter block. So this is the part that makes our test frequency that we then transmit to the phone to generate these harmonics. It starts with a VCO PLL, which generates the test signal, is then amplified by a custom dual stage RF amplifier that we designed. And then since the amplifier has some nonlinearities of its own, we use a low pass filter to remove those so that we don't accidentally receive harmonics that we generated. This goes into a log periodic antenna, which then illuminates the system. On the receive side, we have a HAC1 RF software-defined radio that will analyze these signals. But first, the harmonics from the test device are received by a log periodic RX antenna. If the test signal that we sent out is too high, it will be filtered by it'll be filtered with a high pass filter. Next slide. And then again, and then finally we have Danny, go back one. The whole system is powered by Makita rechargeable battery that allows for modularity so you can swap out batteries on the fly. One more slide. And then finally, our whole system is processed and controlled by a Raspberry Pi, and an LCD touchscreen will allow the user to view the data and give input. So for our first test, what we need to do is we need to generate a signal for this test. And to do that, we chose a 915 megahertz, which is one of the frequencies in the ISM band. And the ISM band is basically a band that the FCC has allocated that you don't need a license for. So if you didn't use ISM band, if you use some other frequency, you would need to license this, and that would raise the cost. And so our test was generate 915 megahertz at or under 1 watt, which is the allowable power. So to do that, we got an analog device ADF4360, which is a VCO that can generate 915 megahertz. And we did a test, and we were able to find out that we were able to comply with this signal span and with a power about 1 dB, which is within the ISM band. And then the next part is we can amplify that up to get a higher signal. In terms of antennas, we chose 2 log periodic antennas, mostly because on the receive side, we needed a large bandwidth to receive the harmonics. We found out that generally their through power is decent in the terms of transmitting and is very good at receiving the harmonics. And this means that all the power sent into the antenna, most of the power sent into the antenna is actually transmitted out to the device, and most of the power received is received into the system.
So once we were able to confirm that we could generate our 915 megahertz signal, the next step was to amplify it. And given the FCC limitation of 1 watt deliverable to the antenna, we were aiming for a gain of around 30 dB, given our 0 dBm input. This is the base amplifier design that we transferred to a PCB design that we ordered and tested. Once all the components were soldered on and tested, I found out that there was a flaw in the design. Initial results show that our amplifier was in fact an attenuator, resulting in a gain of about minus 10 dB. Danny, if you could go one sec. While debugging the circuit, my test points showed me that the amplifier wasn't being biased correctly and that the DC voltage was leaking into the test systems. This circuit shows the addition of decoupling capacitors at the input and output, which resulted in the correct biasing values for the transistor. We were able to achieve gain and consequently produce a working amplifier. The gain was insignificant, however, at only 8 dB, so it required another alteration. Through further simulations, I determined that the frequency response of the amplifier was not correctly suited for our operational frequency of 950 megahertz. The simulations and testing allowed me to determine the correct inductor values necessary to optimize our gain, which are shown here. This circuit resulted in a gain of about 12 dB. This gain was a good result. However, for application, we were going to need more. So I opted for a cascading amplifier design shown here, along with another decoupling capacitor that did increase the gain to about 16 dB, but not to the extent that was expected or necessary. I believe it was due to limitations of the transistor that I selected, but it was not the final design. So in order to increase the power output, I redesigned the biasing network to allow a higher supply voltage going from 9 volts to 11 volts. This circuit reflects the new biasing network and ultimately resulted in a gain of about 18 dB. The last step was to work on designing a matching network at the input and output to optimize their power delivery. The end result produced a gain close to 20 dB, which is less than our desired 30 dB. However, the gain was sufficient for our application. For the matching networks, I decided to focus on using a low-pass filter configuration, an attempt to filter out frequencies that are greater than our 950 megahertz signal, such as harmonics. To find the correct matching network, I began by adding components to the amp in a low-pass filter configuration and then measured the S1 values. The Smith chart diagram with the arrows is a visual representation of what I did to find a match. Given the observed measurement point, I was able to tell how the series and shunt components needed to be altered to get closer to the 50 ohm match. Ultimately, I ended up with a network that produced the S11 value that is shown on the Smith chart in the bottom right corner. The red diamond represents the S11 value before the matching network. The orange line reflects the S11 change from the series inductor, and the blue line represents the change from the shunt capacitor. The yellow diamond is the final S11 value that we were able to achieve with the matching network. According to the measured S11 value of minus 19.58 dB, we observed a reflected power of about 11 microwatts. Given our input power of 0 dBm or 1 milliwatt, we were only losing about 1.1% of our input power, which we found acceptable for our application. For the output match, through the same measure and alter methods, I was able to come up with the matching network that produced the S22 value that is shown on the slide. The closeness to a 50 ohm match was a satisfactory result since this was the output measurement of the amplifier and would ultimately go to our antenna that had an impedance of 50 ohms. Again, the Smith chart shows the starting S22 measurement, and the orange and blue lines show how the series inductor and shunt capacitor helped us get close to a 50 ohm match. So once the amplifier was matched and designed to a point that we thought was suitable, we conducted an S21 measurement to see how the amplifier performed given a range of input frequencies. As you can see from the S21 measurement, the amplifier is letting our frequency of 950 megahertz through and is filtering the higher frequencies. My test system calculations allowed me to determine an overall gain of 20.65 dB at 950 megahertz with an input power of 0 dBm. We were ultimately transmitting a power of about 116 milliwatts, plus or minus half of a milliwatt due to potential measurement inconsistencies and limitations of the test system. My efficiency calculations say that it operates with about 8.8% efficiency. And according to research, the theoretical maximum efficiency of a Class A linear amplifier is 25%. However, realistically, they are only 10 to 20% efficient. We are below the typical minimum. However, we were satisfied with the result. So once we had our final amp design, we wanted to see if we were still operating linearly. Our gain compression test showed us that we were operating outside of the linear region and in fact compressing. This was an issue for our application because by compressing the amplifier, we're consequently transmitting harmonics. The filter matching networks are helping to mitigate this issue. However, we opted for an additional filtering process. Also, the flurpy or dip in the compression curve is indicative of oscillation. However, it isn't at our operating input power of 0 dBm. So since it wasn't at our input power, it wasn't a direct issue that needed to be resolved. Given more time, this is something that I would have gone back to fix.
So in order to lower the power levels of the harmonics we created, we tested a commercial low-pass filter and we connected it to the output of our amplifier. With this low-pass filter, we noticed that the attenuation of the second harmonic was about negative 56.4 dB, and at the third harmonic, it was about negative 51.8 dB. Now, in order to calculate the full transmitter harmonics, we also had to account for free space path loss. We did this by calculating the free space path loss at about 6 inches distance from our device under test. This was in accordance to our engineering requirements. We calculated that the second harmonic, the free space path loss, was about 9.35 dB, and with the same measurement at the third harmonic, it was about 12.87, meaning that the total harmonic attenuation at the second harmonic was about negative 65.7, and at the third harmonic was about negative 64.6. For a receiver, we opted to use a software-defined radio, or SDR, as receiver front end. Testing with this SDR revealed the ability to observe harmonic backscattering. The SDR can easily be sampled using these available software libraries to process backscattering frequencies for power changes, which then indicate a nonlinear junction. We conducted the test with our entire system to see what we are receiving results, and we expect to see that the second harmonic is greater than the third. And with the SDR, we were looking at the second harmonic, and the first point is without the presence of a device under test. Without the presence of the DUT, it was about negative 70.6 dBm. Then when introducing a DUT, it was about negative 64 dBm. With this inherent spike, DC spike that we got from the SDR, we calculated that the receiving harmonic power level was about 6.6 dB greater than the spike. And if we were to neglect this DC spike and our presumed noise floor, we assume that the harmonic power level is about negative 114 dBm. Now we did the same process, but this time at the third harmonic. In the third harmonic, the power level is about negative 63.4 dBm without the presence of a device under test. And then with the introduction of the device under test, it went up to about negative 57.9 dBm, which is about a harmonic increase of 5.5 dB. Again, if we were to neglect the DC spike and a presumed noise floor, we can assume that the harmonic power level is about negative 115 dBm. And our results showed that the received harmonic levels were consistent with what we expected, and that the third harmonic is less than the second.
So one of the key requirements that the client requested was that we have minimal controls and not need engineering background to operate this device. And particularly, he didn't want any audio because this would alert inmates if they were running this test. So we designed a rather simple Python GUI that would run on the Pi that would be able to be used on the touchscreen. It's dynamic, so if you could put it on any screen that gets attached to your system to improve modularity. A single button activates a nonlinear junction scan, and then it has easy to read test indicators. So this is just another example of it in running in a test mode. In this case, you can see it just has test indicators if it's running, and then shows the confidence level of detection, low, medium, high. In the settings button, you can set different thresholds for the level of confidence. So you could say a 3 dB increase, a 5 dB increase, a 12 dB increase, and that will allow you to adjust for whatever your situation is.
So our next test was to test our battery system, and this would fulfill our engineering requirements 6 and 7. The way we did that is we wanted to test if the system can operate on the battery power for at least 4 hours, which equates to about half a duty shift. We did this by first measuring the power usage of the system. We then measured the efficiency of our power regulators. With these results, we would select the capable battery based on the requirements needed from our tests. And then these tests would prove that the device can operate for the sufficient amount of time, which is at least 4 hours, to conduct our nonlinear junction tests.
So what we did is basically we took each of the devices and ran them on their own power supply and then monitored them. And from this, we basically figured out that our total system power for about 4 hours would be 25.7 watt hours in a worst case situation where it was the duty cycle was 100%. But we also realized that in our system, the power regulator that we chose isn't, in no case, is 100% efficient. So we used a dummy load to simulate power that was slightly higher than our actual system load. And we found that the regulators that we had chosen were about 73% efficient. So then adding on that efficiency, or using that efficiency to calculate the actual time, we determined that we would require about 44.3 watt hours for a 4-hour use period. Based on this, to fulfill the requirements, we chose a Makita-styled battery that's 12 volts that we could then regulate to the system power, and it was rated for about 72 watt hours.
To fulfill engineering requirements 7 and 8, we designed an enclosure in Fusion 360 to house our system so that an officer could easily use the device while conducting their searches. The design evolved from the way that each component interfaced with each other and from the size and shape of each component. The final design is pictured here, where the transmitting and receiving components are in one case, the antennas face forward towards a target device, and there is a location in the handle for our tool battery. Once the final design was agreed upon, we began printing. We comprised a detailed parts list of our enclosure in case one wanted to know how long it would take to replicate this design. Overall, it would take about 3 days of printing time by printing one piece at a time with 20% infill and 0.2 millimeter layer height, which are typical print settings. These are images of our actual system that we were able to create, and we were happy with the accuracy of the design. Everything fit and moved together well, and we were especially happy with the way that the battery fit in the handle, which you can see that it's at the bottom standing on.
So for the project conclusions and kind of our future works, one slide, Danny. we were able to successfully test the engineering requirements for the actual source generation. Next slide. We were able to choose antennas that would allow for both the source transmitting and harmonic receiving. And then finally, we were able to prove that we were able to actually analyze and determine a difference between electronics in the lab and using our system. And then finally, we were able to do some tests to figure out the battery requirements and then the actual regulator efficiency for our battery time requirement. The one thing that we did run into challenges with was the fact that because we couldn't have all the system together during the pandemic, that we couldn't do a full system integration. So some of the software processing that we would like to have complete at this point wasn't completed. However, we were able to complete the backbone for our user interface and some of the functionality controls that could be combined in the future to provide a full system. Finally, for our requirement for our budget, we took up all the we took a list of all the devices and components that we used to create one product, and we found that we came out to $697, which comes under our $750 budget. And so this was our original schedule that we started with. Basically, what we found out was very early on, and almost around December, we did a viability test, and we found out that at first we thought this wasn't going to be possible due to how hard it is actually to detect these harmonics. So we kind of moved back and rescoped, and that's where we went to our more modular form where we could upgrade this device. And then throughout that process, up in around the first and the second, we were able to complete most of our development and testing. However, when the pandemic hit around March, then we were unable to complete a lot of integration and testing due to different components being at different team members' houses. But overall, we were pretty confident and happy with our ability to complete components that allowed us to prove detection of these devices.
And these are a couple of supporting courses that helped us along the way, along with some references. And we want to give special thanks, everyone. And I'd like to especially thank our advisors, Dr. Mohammed Salem and Mr. Chris Stewart in RSV, for the knowledge, support, mentorship, and resources throughout the program and our senior design project. And I want to thank all the faculty and university employees that have been our mentors and friends throughout our university career. And of course, we want to thank our families and friends for their continued support. And thank you everyone for listening, and have any questions or comments?
Thank you. Just a quick reminder again to complete the evaluation form for this team also. The link is still the same. There are 4 options to choose for the team. And please choose this team is the CellSight. Thank you for completing the evaluation form. Now it's time for question and answer, and I see Rob for first question. Rob?
Okay, I'm unmuted now. Great work, guys. Really interesting. I'm particularly interested in the SDR, not surprisingly. You mentioned that you had a noise floor of minus 130 dBm. I'm sort of surprised at that. I'm not quite sure what you mean. Is this the displayed average noise level if you were to use spectrum analyzer parlance? Because the HackRF is only an 8-bit SDR, and so theoretically it's only got 50 dBm dynamic range. Did you look at other SDRs, and would extra dynamic range by using a 12 or a 14-bit SDR have improved your performance, do you think?
Yeah, so when we were looking at the SDRs originally, we wanted to use something a little cheaper because the Hack1RF is pretty expensive. And what we found is actually even the really high quality SDRs are 8-bit resolution in their sampling. However, they're able to get around this by doing more averaging and having more low noise components.
Okay, thank you. Next question, Joe.
Yeah, so you guys mentioned that you wanted this to be used by jail personnel. On your GUI, you mentioned in the settings that there's a dB setting. Could you give me a little bit more information on how that works? And if it is just a straight number, how do you expect that to be usable by jail personnel who are not electrical engineers?
Right, so the thought about that is more for our own testing. When you're calibrating in the lab, certain devices will give back more power than others. And in the case of our project and the scope of our project, because we didn't have the full time to complete processing for it, we wanted to give people the ability in the future to set their threshold when they complete this, since we couldn't do the full system test together. But in the case of like in a jail in the future product, that setting wouldn't be used unless they're trying to recalibrate it if something were to go wrong.
All right, thank you.
Thank you. Next question, Casey.
Thanks. First of all, bravo. This is one of the most impressive projects that I've seen, and I've been watching a lot of these. It seems like you guys really understood your requirements and how to translate that into some engineering testing, and I was really impressed with all that. Can you guys just comment a little bit on your team dynamics? Did you have like a clear leader, or was it all you guys just working together? And how do you think your team dynamics resulted in a good outcome? Thank you.
So I felt like overall it was a pretty stressful process. It was a long-term project that was a difficult project. However, I felt that our team dynamic overall felt pretty good. I wouldn't point out to say that there was one absolute leader, because over the process of the project, there were times where some people or one of us would step up, the other two would kind of take a back seat, and then it would sort of cycle through that depending on the situation or the status of our project.
Yeah, and to add on to that, there was definitely times when one person would help the other ones through, and then someone else would come up and then push through a tough patch. And overall, it was really nice because we were able to break up a lot of different components of the project into areas that each one of us was interested, whether Blake took on the RF amplifier side or I took on the source generation side. So it was really nice to do that.
What are your thoughts, Danny?
Yeah, like I agree with David and Blake. It wasn't necessarily a one time where like for a specific lead, we did balance out a lot of the work. Like if I was working on software, Blake was working on the amplifier, or David the source generation. I think we all did like a good job of helping each other whenever there was issues. Like I know with the amplifier, Blake, I did have Blake out a little bit with the amplifier, but again, we were all pretty much good at working together and helping each other out whenever needed. I know I did run into some issues with the software, and then David was really helpful with his experience with Python on helping getting the GUI working. And overall, we just all did a great job of working together, and everyone, just working together really well.
Great. Next question from Siva.
Thank you. Great job, guys. I think great presentations. I have a question that I'm curious regarding this interference, RF and EMI, whether if at all, if it is required for your class A, it's not that much human, but what is your study shows whether you required RFI EMI shield, especially when you are working under 116 millivolt at 950 megahertz frequency,
Yeah.
Go
ahead, Blake.
So throughout the process, as we were meeting with our instructors, one of the concerns was the amount of interference that we would get, since we had an enclosure and we're probably going to have a lot of noise leaking into the system. So that was probably something that we were going to deal with once we got close to the end of our project. However, given the circumstance, we never really approached it. However, it was a concern and something that we were planning on handling.
Okay, good. Next question, Chris.
Hey guys, good job. You did a great job trying to pull off a very difficult problem in the beginning of this stuff. So congrats to getting this far. So same question as last time. What's the most important lesson you learned through the whole process for each of you?
Yeah, two things. One was making sure we're not doing as much documentation as we wanted to, and then kind of having to bite the bullet on that. So I know that there's some juniors in the video here. Make sure you do documentation as you go, which is something that Chris will tell you. And then the second thing was thinking that things were going to go smoother than they were, and ending up hitting road bumps where there was lacks of knowledge that then had to be overcome, which caused part of the project to go longer than expected. So being able to manage your time is something that I think was hard, but it was really well learned in this project.
Yeah, I agree with David. I know we didn't document as we went as much as we should have. I know you tried to tell us that we should have documented, worked on it for it, and done everything as we go. And then once this pandemic hit, we were racing to try to grab test results or any kind of like progress results we had, and then since we didn't document it as well as we should, we were unable to find it. We were like having issues with that. So I think if we would have listened a lot more when you were telling us to document or prepare these slides that you go, I think it would have helped. We would not have run into those issues.
Yeah, aside from all of the engineering aspects that we learned, like I feel like we all learned a lot. Prior to starting this project, we all had minimal RF experience, but we kind of jumped into the deep end on this and learned a lot consequently. But aside from that, I think the most important lesson for me was the difficulty in scoping out a long-term project like this, like being months out and trying to determine what you could have done, say in 6 or 7 months, because when you scope out a project timeline, you're kind of assuming a lot of things to happen correctly, such as parts being ordered or not running into obstacles that are unforeseen. And then also handling things correctly and adjusting the scope of your project when things like that do occur. Because I don't think any of us had a pandemic on the schedule, but we did the best that we could.